the expectation of the exponential function. You're going to call it as a characteristic function. So the characteristic function will take the product of the n random variables it will take here. For example, if n is equal to 2, so there will be a pi x of j omega into pi x of j omega will be there. So that one you are going to call it as a two random variables will be called here. The product of two random variables you are going to consider. So right. So done, right? So this is the expectation function we'll call here, and also we are going to take that the central limit theorem you are going to consider where for the random variables. So you are going to take the average you are going to take here, average you are going to take, and the mean and variance of that one we have seen in the last classes, and also we have seen on problem also we have seen in that one. So the problem is somewhere here. So we are saying the problem and that also we have seen here. Okay. So this is a problem. Yeah. So this is a problem. We have seen the problem on that one also, and we have summarized the list of the formulas. ಬರ್ತಿದೆಯಾ ಸರ್?
ಬರ್ತೈತೆ ಸರ್.
ಹಾಂ ಸರ್.
ಸ್ವಲ್ಪ ನನಗೆ ಇದು ಕ್ಲಿಯರ್ ಆಗಿ ತೋರಿಸಿ.
ಹಾಂ ಸರ್.
ಸಾಕು. ಥ್ಯಾಂಕ್ ಯು ಸರ್.
ಓಕೆ ಸರ್. Shall I continue, sir?
Please continue.
Okay. Thank you, sir. So in the last class, we have seen the summary of the formulas we have seen, and we have seen on problem, and that also we have seen here. So where we have taken the 120 random variables we have taken, 120 random variables we have taken. For that one, we have find the mean of the IID random variable, and also we have seen the mean of the central limit theorem. Also we have seen. I told you to calculate this one. I think you have calculated that one. Okay. So those things we have seen in the last classes. Now let us continue from this one. Okay, so I'm going to take the new concept I'm going to take where already we are discussed in the module 1. The extension of the module 1, we are going to do that one here. So that one you are going to call it as it's a conditional probability we are going to call here. So take the next topic, which is called as a conditional probability. So you're going to take the conditional probability for the bivariate random variables you're going to take here. So where the two random variables will be considered here. So bivariate random variables you are going to take, where we are going to consider the two random variables you are going to consider, right? So here what you are going to see is in the module 1 already we have seen the conditional probability here. So just I'm going to recall the topic what we have seen in the module 1. So suppose if the event A is there and there are two events are there, assume that the event A and event B. Suppose if the event B is already happened and the occurrence of the event A depends on the occurrence of the event B, that one you are going to call it as a conditional probability you are going to call. So that is the probability of occurrence of A, this one you are going to call it as a probability of A given B. So this is called as the probability of A intersection B divided by the probability of B we are going to call here. So this is a conditional probability what we have seen in the generalized probability terms. Okay. And also we can write the similar way we can write as a probability of B given A, which will be equal to the probability of A intersection B divided by the probability of A. Okay. So this is a conditional probability in which the occurrence of the event A depends on the occurrence of the event B that has already happened, and also it depends on the joint probability of the event A and event B as occurred here. Okay. So now what I am going to do, so already we have seen this concept in the module 1. We are going to extend the concept for the two random variables you are going to extend here. We are going to extend the concept for the two random variables. That way it is called as a bivariate random variables you are going to call. So let us recall the topic here, right? So what I'm going to do is I'll define the conditional, the CDF of the two random variables x and y we are going to define here. We are going to define the conditional cumulative distribution function of the random variable x and y depends on the event B that has already occurred here. Okay, so let us take that one. For the bivariate random variables, 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 the joint CDF. So CDF is nothing but it's a cumulative distribution function. Already you know. the joint CDF conditioned by an event B by an event B is given by for the bivariate random variables, we are going to consider the joint cumulative distribution function. You are going to consider that is for the random variables x and y. We are going to consider so that is depends on the event B we will consider here. So under this section, what you are going to see is we are going to define the formulas for the CDF and also the PDF for the conditional random variables you are going to define here. So what you see in the module 1, the same thing you are going to extend here. So here I'm going to consider the cumulative distribution function of the, it is denoted by capital F of x comma xy. So conditioned on the random variable B, condition on the event B that has happened here, event B that has happened, it is going to be denoted as fxy of x comma y given B. So the event B has already happened. So you know how to define the fxy of x comma y. So this will be defined as the probability that, okay, so x can take the value less than or equal to the small x here. So your capital X can take the value less than or equal to small x. Intersection of y can take the value less than or equal to the small y. Okay, so this is nothing but fxy of x comma y. So we are going to take the condition of that one. So that way we are going to take as a intersection of event B. We are going to take here intersection of event B. Why? Because it's a conditional random variable we are considering. So that's the intersection of event B. So divided by the probability of B here. Probability of B. So just you can see, compare this formula with this formula. So both are one and the same, you can see here. So since we are considering the probability of A given B, so A given B is nothing but it's a probability of A intersection B. So same way here also we are going to take here. So fx of x comma y is nothing but it's a probability that fx of this can be defined like this here. Probability of x is less than or equal to x, intersection of y is less than or equal to y, and intersection B z, the same thing you are going to consider divided by the probability of B. So that one, so this is called as the cumulative distribution function of the random variable x comma y given the event B has already happened here. So done, right? So any doubts in this one? Any doubts in this one? So what you are going to see under this topic is, yeah, and what you are going to see is we are going to define some formulas. We are going to define, that's it here, nothing else. So what the formulas you see in the module 1, the same formulas you are going to define here. Okay, this is the one of the formula which is going to denoted by the CDF here. Now let us take the PDF of this one here. So I'm going to define the conditional joint probability. I'm going to define for the random variable x and y, that is the PDF. The PDF can be obtained by differentiating this one here with respect to the x and y here. So you can take the joint PDF conditioned by an event B, is given by so here what we are going to do is, so in order to obtain the PDF, we are going to differentiate the CDF here. So it will be defined like this: fxy of x comma y given the event B will be equal to the, so del square we are going to differentiate 2 times here. So it is del x into del y. So it is fxy of x comma y given B. So if you're going to differentiate this one with respect to the 2 random variables x and y with respect to the del x and del y, we are going to get the PDF you are going to get here. PDF is nothing but it's a probability density function here. Probability density function. Done, right? Now here the B is nothing but it's a event B here that will be defined as probability of B. So this probability of B will be defined like this here. So you can take the next formula. The probability of event B, the probability of event B is given by, so the probability of event B is given by, so the probability of B is nothing but, so we're going to take it is given by, so it is obtained by integrating the CDF, that is the PDF of the random variable x and y with respect to the dx and dy. We are going to get the probability of B within the limits of the B here. So within the limits of B, dx and dy. So this will be defined like this here. So something, this is the curve it will take here. So assume that this is the intersection of the x and y axis, x and y points here. So this is x and this is y. So this is the thing at the, it's a x comma y, where the probability of the event B has been defined here. The probability of the event B has been defined. Got it now? So like this, it will be defined. So this can be obtained by within the boundary of the event B. So if you are going to integrate the PDF with respect to the x and y, we are going to get the probability of B. We are going to get here. Okay. So we can define the condition random variable similar to this manner. We can define the condition random variable. So similar to how we are defined the probability. Okay. So I'm going to define the condition random variable will be like this here. So you can take the event B. You can take the one sentence here. So just in the under this section, we are going to define the formulas for the each and every concept like PDF and marginal PDF. We are going to define the formulas here. So these formulas, it has been extended version of the what we are seeing in the module 1 here. If you have any doubts at any particular point of time, you can ask me. So I can take the event B.
Oh.
Yes. Take the event B. The event B takes the role of sample space for the conditional random variables for the conditional random variables. So here, whatever the event B you are defined, so this is going to take the role of the sample space it is going to take here. Okay, that is for the conditional random variables. So now what we'll define is we are going to define the formula for the conditional PDF we can define here. So you can take the conditional PDF is given by the conditional is nothing but the occurrence of the one event depends on the occurrence of the other event. You are going to call as the conditional probability you are going to call here. So the conditional PDF is given by the conditional PDF is given by. So you can take fxy of x comma y given the event B. So it is the thing but so usually it will be defined like this. So it is fx x comma y, so divided by the probability of B. So this follows the formula which we are defined here. The similar way it is going to follow the same formula is going to follow here also. So here in which x comma y belongs to the B and so belongs to the event B here and it will be 0 otherwise here. So this is extension of the conditional probability. So done. Okay, so from this conditional PDF, we can able to obtain the marginal PDF we can able to obtain here. So marginal PDF is the thing. So this is the PDF of the bivariate random variable here, bivariate random variable x and y. So from this one we can able to obtain the PDF of the single random variable that is x of x we can obtain here or y of y we can obtain here. That one you're going to call it as the marginal PDFs you're going to call. So we already seen that one here. So how to obtain that one? As usually we are what you are going to do is we are going to integrate this one fxy of x comma y with respect to the other random variable. For example, if I want fx of x given b, I want means I'm going to integrate this one with respect to the dy we are going to integrate here in order to get the conditional PDF here of the single random variable. So let us take that one. Getting the concept here now. So so I'm going to just recall what we have seen so far. So this is the conditional probability, how it has been defined. We considered it. Yeah, sir.
Sorry to disturb you.
Yes, sir.
In which module you are teaching?
So in the second module, last topic I am doing, sir.
Course outcomes ಯಾವ್ದು ಬರುತ್ತೆ?
So course outcomes, the defining of the bivariate random variables, PDF and CDF and the joint conditional probability ಬರುತ್ತೆ sir.
ಅಲ್ಲ CO2 ನ CO3 ನ
CO2 ಬರುತ್ತೆ sir.
CO2 ನ ಬ್ಲೂಮ್ಸ್ ಟ್ಯಾಕ್ಸಾನಮಿ ನಲ್ಲಿ ಯಾವ ಲೆವೆಲ್ ಅಲ್ಲಿ ಬರುತ್ತೆ? ಯಾವ ನಾಲೆಡ್ಜ್ ಲೆವೆಲ್ ಬರುತ್ತೆ?
ಲೆವೆಲ್ 2 ಮತ್ತೆ ಲೆವೆಲ್ 3 ಬರುತ್ತೆ ಸರ್.
ಲೆವೆಲ್ 2 ಮತ್ತೆ ಲೆವೆಲ್ 3 ನ DSP ಅಲ್ವಾ ಸರ್?
ಅಲ್ಲ ಸರ್, ಇದು ಇಂಜಿನಿಯರಿಂಗ್ ಸ್ಟ್ಯಾಟಿಸ್ಟಿಕ್ಸ್ ಸರ್.
ಇಂಜಿನಿಯರಿಂಗ್ ಸ್ಟ್ಯಾಟಿಸ್ಟಿಕ್ಸ್ ಸರ್.
ಹಾಂ ಸರ್. ಕಂಟಿನ್ಯೂ
ಮಾಡಿ.
ಓಕೆ ಸರ್. Okay, so I'm going to recall what we are doing so far here. So this is the conditional probability we have seen here. So under that one, we have seen the CDF, we have seen, we have defined the formula for that one, and we have seen the PDF, and PDF is obtained by differentiating the CDF. And similarly, we have defined the formula for the joint conditional PDF we have defined here. Now what I'm going to do is I'm going to differentiate, integrate this one with respect to the random variable y or with respect to the dy in order to get the marginal PDFs. So that one let us see now here. Okay. Is it okay? Any doubts so far? Can you hear me my voice, right?
Yes, sir.
My voice is audible, right?
Yes, sir.
Yes, sir.
Any doubts so far?
Yes.
Okay, fine. Okay, so now let us see the conditional PDF here. You can take the conditional
No, sir.
joint PDF. So the conditional joint PDF. The conditional joint PDF is integrated with respect to the is integrated to obtain the conditional PDF of single random variable given by so you can take this one. So it is fy of y given b. So I want to obtain the marginal PDFs. So marginal PDFs is the thing, but the single PDF you're going to call it as a marginal PDFs here. So if you're able to obtain the single PDF from the joint PDF, you're going to call it as the marginal PDFs you're going to call here. So how to obtain that one is so integrating with respect to the joint conditional PDF here. So this is the joint conditional PDF with respect to the other random variable. For example, if I want the fy of I need to integrate with respect to the dx here. If I want fx of x, I need to integrate with respect to the dy here. Okay, so this one we're going to obtain here. So if I'm going to integrate here, so what will be obtained is, so the integral part we are not going to consider, just I'm going to define the formula. So if I go take the integration, it will become so a bit lengthier. So this will be defined as so fxy of x comma y given b. So this is the thing, but already we have defined that one. So this is the thing, but probability of b. Okay. So here what you are going to do is, so since we are want with respect to the dx, so I am going to define with respect to the conditional, the single PDF fx of x you are going to define. Okay. So now the steps will be like this you are going to do. So what you'll be doing is, so I'm going to equate the b to the, we are going to equate the dx to the, so just as dx tends to 0, what will happen is, so the b will become equal to the small x, it will become here. So b tends to the random variable x, it is going to become, so right. So what you are going to do is, suppose if your dx tends to 0, so since we want the conditional PDF in terms of the random variable y or x we want here, so that's why you're going to make the small correction you are going to make here. What that one is, as dx tends to 0, the event b tends to the x, it is going to tend here. So we can define in terms of the conditional random variable can be defined in terms of the random variable x and y, like this we can define here. So if I want b, we can keep like this, b also we can keep it here. So if I want in terms of the random variable x and y, what you are going to do is you are going to replace the b with the x we are going to do replace here. Okay, so at that time, so this has become fxy of x comma y. Okay, so divided by fx of x here, divided by fx of x. So this is what we seen in case of the module 1. In case of the conditional PDFs, we have seen that one here. So here I'm going to change the variable b to the variable x we are going to change here, so that we got this one here. So right, you can see, right? So done. What I did is I changed the random variable b to the random variable x we are changed here. So we got the marginal PDFs we got like this here, marginal conditional PDFs we got like this. Okay, so this is the for the single random variable we are defined like this. So similarly we can extend this one for the other random variable. So you can take similarly, so we can define for the random variable x here. So it is x given y. So it will be equal to the fxy of x comma y divided by fy of y, fy of y. So this is for the other random variable x. We can define like this here, fx of x given y. Done, right? Okay, so we define the joint conditional PDF. We have defined the single marginal conditional PDF. We have defined for the random variable x and y here. Now from this one, so we know that if you are going to integrate the PDF, we can able to obtain the CDF here. So let us see the conditional CDF here. Okay, so if you are going to integrate the probability density function, we can able to obtain the cumulative distribution function. We can able to obtain here. So let us see that one here. Okay, so you can take the conditional CDF. The conditional CDF of single random variable is obtained by integrating conditional PDF, integrating conditional PDF. So that is given like this here. So if I want the PDF of the single random variable fy of y given x, so it will be given. So integral from minus infinity to the y fy of u given x into du. So with respect to the random variable du, we are going to integrate because already the upper limit is y here. That's why if I'm going to replace u with the y, we are going to get the fy of y will get here. That's why when you are doing the integration, we'll be doing like this. So right. So fx of. So similarly, we can give for the other conditional random variable. We can be given like this. So you can see, right? Okay. So sometimes internet will connection is low. So at that time it will be blur. Okay. So similarly, I'm going to define. So minus infinity to the y. So fx of u given y. So with respect to the random variable du, we can obtain like this here. Done. Okay, so far we have seen the conditional PDF. We have seen the conditional marginal PDF for single random variable. We have seen, and the conditional CDF we have seen here. Now let us see the expectation of this conditional PDF. Let us see it here. Okay, let us see the expectation of the conditional PDF. Let us see that one here. So why do we need the expectation? Is because here. So as I told, the application of this one we can find, especially in case of the digital communication, we are going to find here. So okay, suppose in case of the modulation technique, which is called as the binary frequency shift keying. So there will be different frequencies you are going to use for the transmission of the data 1 and data 0 here. So at that time, so when you are transmitting the data 1, so it is conditional on the data 1 transmitted and it will be received as 0. So there we are going to make use of this conditional PDFs we are going to use here. So at that time it is required to find out the mean of that one. It is required to find out the variance of that one here. Why? Because if I transmit the symbol 1, the symbol 1 will be transmitted with a certain voltage, and similarly the symbol 0 also is going to be transmitted with the other certain voltage here. So in those cases, so it is required to find out the mean and variance of that one. So by making use of that one, we can able to find out the probability of error, which is the main important criteria in case of the any modulation techniques. So that will be considered as a performance analysis of the modulation techniques will be taken, right? So in such cases, these concepts it will be useful here. Now let us find out the mean, variance, and some the conditional that is called as a what do you call as a okay. So conditional this one you are going to call. So that is called as a just a minute. That is called as a conditional characteristic function you are going to define here. Okay. So let us find that one. So you can take the conditional expectations. The conditional expectations of the conditional expectations are given by the conditional expectations are given by. So here we need to define the conditional expectations here. So conditional expectations is nothing but the expectation is nothing but it's a mean of the random variable you are going to consider. So let us take, we are going to take like this here. So the expectation of the some function I'm going to call the function is nothing but g1 of y. So already we are seeing in the module 1. So given the random variable x here, so this is the conditional random variable you're going to consider here. So g1 of y, given that x has already happened. So this is nothing but expectation is nothing but it's the integration of the random variable g1 of y with respect to the conditional random variable. So that is given by since it's a given x is there, so we are going to take the fy of y given x with respect to the dy we are going to consider here. So whatever the numerator will be there, the denominator, the same expectation you are going to take here. So same CDF you are going to take here. So similarly, the expectation of the other g2 of y with respect to the y we are going to take in here. So conditional random variable y. So this is given by so g2 of y. So it is equal to the fx of x given y here. So since it's a given y is there, we are going to take with respect to the conditional with respect to the random variable y. So we are going to integrate with respect to the dx here. Right. So this is the expectation we are going to call here expectation. So you know expectation is nothing but it's an integration of the corresponding random variable with the corresponding PDF will be taken here. Done, right? It's visible, right? So can you see?
Yes.
Okay. So done. Now let us find out the mean of that one here. So mean of that one we can take the conditional mean is given by the conditional mean is given by so I can take the conditional mean is given by the conditional mean is given by. So we're going to find out the mean of the random variable y given x here. So this is nothing but so we are going to integrate this one with respect to the that is the random variable y with respect to the fy of y given x we are going to integrate here with respect to the dy. So this is called as the conditional mean you are going to call the conditional mean. So similarly we can able to obtain the conditional mean of the other random variable. Okay, so let us find out that one. So that is new x given y, which will be equal to the integral from minus infinity to plus infinity. So x into fx of x given y into dx here. So this is a conditional mean we are going to obtain for the x given y. Then, so similarly we can find out the variance of this one also. Let us express here. So the variance is nothing but it's a difference between the random variable x and its mean. We are going to call it as the second central moment. You are going to call it as the variance. You are going to call here variance. So let us see that one. So you can take the variance of the conditional variance is given by, you can take the conditional variance is given by the conditional variance is given by. So variance is nothing but so it is going to be at a sigma square y given x. So it is nothing but integral. So minus infinity plus infinity. So it is y minus. So it's a difference between the second central moment. Second central moment is nothing but it's a difference between the random variable y and its conditional mean. The conditional mean is nothing but y given x the whole square into the conditional PDF we are going to take y given x into so dy here. The conditional PDF you are going to take. So right. Done, right? Now similarly we are going to take the conditional mean for the random variable x given y, that is the sigma xy square. So it is the integral. So x minus mu x given y the whole square into fx of x given y into dx here. This is the conditional variance for the random variable we are going to define here. Right. Okay. So similarly, we can define the conditional characteristic function we can define here. So you can take. So these are some formulas we are listing for the random variables
Yes, sir.
already, which we have seen, which we have seen for the different random variables. So here also we are seeing for the conditional random variables. So in the beginning we are seeing for the normal joint PDF we have seen here. Afterwards we have seen the mean, expectation, everything for that one. So afterwards we have seen for the normalized Gaussian random variables we have redefined the same formulas. Now we are going to redefine the same formulas for the conditional random variables we are redefining. Just we are changing one term we are changing, that's it here, nothing else. So right, so I can take the conditional characteristic function is given by the conditional characteristic function is given by characteristic function is given by. So we are going to define the conditional characteristic function. So you know characteristic function is nothing but the expectation of the exponential function. We are going to call it as a characteristic function here. So it will be defined like this. So phi of y given x of j omega. So this will be equal to the integral from minus infinity to plus infinity. So f y of y given x into e to the power of j omega y into dy. Okay, so similarly phi of x given y of j omega. So this also be defined like this here. So fx of x given y e to the power of j. The expectation is nothing but, so it's nothing but product of the PDF with respect to the exponential function. So that is the conditional characteristic function we can able to obtain. So it is j omega x into dx. J omega x into dx. So the characteristic function itself is nothing but it's an integral of the PDF with respect to the exponential function. That one you're going to call it as a characteristic function you're going to call here. So since it's a conditional, that's why you're going to take the conditional random variable with respect to the exponential function. We're going to define the conditional PDF, that is characteristic function we're going to define here. So right, done. Okay. So now in the module 1, we have seen the base rule we have seen here. So base rule, what is that? The base rule is nothing but, so okay, so we are going to call the base rule. So what we are going to call that is the base rule is nothing but, so it says already we have seen in the module 1 here. So it says that suppose if I'm having the probability of A given B, so this is nothing but the probability of A intersection B, so divided by the probability of B we are going to call. So this implies that the probability of A intersection B, so this will be equal to the probability of A given B into the probability of B. So this is we are going to obtain. Okay, already we have seen this one. So similarly, we are going to call the probability of B given A, which is nothing but the probability of A intersection B divided by the probability of A here. So this implies that the probability of A intersection B, which will be equal to the probability of B given A into the probability of A here. Right now, so already we have seen these conditional probabilities you are seeing here, conditional probabilities. Now if you are going to equate these two probabilities, if you are going to equate, so we can able to call that is the probability of A given B into probability of B. So this will be equal to the probability of B given A into probability of A. So this one you are going to call it as a base rule. We are going to call here BAYES is the name of the scientist here. So you're going to call this one as a base rule. You are going to call here. Correct now? Correct, right? So that one already we have seen in the module 1 in the beginning introduction part. We have seen this one here. So I'm going to redefine this conditional PDF in terms of the base rule we can redefine here. So what you are going to do is, so it is fx of x given y. So since the denominator y is there here, so we can make it as the fy of y. So this will be equal to the fy of y given x into fx of x here. So this is in terms of the base rule, we can define the conditional PDFs we can define like this here. Okay, the conditional PDFs has been defined like this in terms of the base rule we can define. Right. Okay, so this is in
Yes,
terms
sir.
of the base. Yeah. And also we have seen that so statistical independent events we have seen here. Suppose if the event A and the event B are independent. So independent. So then what we can see is the probability of A intersection B. So we can write as the probability of A into probability of B we can write here. So right. So this is already we have seen here. So similarly for the random variable X and Y we can say like this. We can take if random variable X and Y, if random variable X and Y are statistically independent. Statistically independent is nothing but there is no dependence on each other here. That is nothing but okay, statistically independent. So for the statistical independent events, we can write like this here. So now already we have defined that one. We have seen the statistical independency, the uncorrelated, many things we have seen here. Okay, so that is fxy of x comma y can be defined as product of fx of x into fy of y here. So this is for the statistical independent events. We can express the joint PDF as the product of the individual PDFs. We can express here like this. So then, so if the x and y are the statistical independent, so then it will become, so fy of y given x can be expressed as the fy of y, and similarly the conditional random variable fx of x given y can be expressed in terms of the fx of x here. So this is if the random variable x and y are statistically independent here. If the random variable x and y are statistically independent, then we can express it like this here. So you can see now. Then, okay. So these are the few formulas which we have. Yeah, these are the few formulas which we have defined in terms of the conditional probabilities, in terms of the conditional probability, in terms of the event B here. So just as recall, what are the formulas we have seen those under the topic of conditional probability for the bivariate random variables. Okay, so we have seen the CDF of the random variable we have defined for the conditional event on the event B here. So similarly, the PDF which has been obtained by differentiating this one with respect to random variable x and y, we can able to obtain the PDF here. That is a conditional PDF. So this one we can redefine in terms of the fxy of x comma y. We redefine in terms like this here in terms of the probability of B. Suppose instead of the event B, if I'm going to take the event x and y as a conditional, I can able to obtain the marginal conditional PDFs we can obtain like this here. Fy of y given x will be equal to the like this we can obtain here. That is for the random variable y, and also for the random variable x we can able to define like this here. So afterwards we can able to obtain the CDF by integrating the PDF here. So this one we have seen, and also the expectations we have seen. So why do we need expectations is because in the digital communication where we need to find out the probability of error. So there we need our expectations, and we have seen the mean of that one. Mean of that one we have seen the variances of that one, and we have seen the characteristic functions. Okay, and also we express in terms of the base rule we expressed here, and also we seen the statistical independent events. So we can express like this, and this is how the conditional PDFs will become equal to the individual PDFs here. So right, so these are the topics we have seen under the conditional bivariate PDFs here. Right, any doubts in this one? So just we are redefine the formulas for each and every topic here. So since from the beginning we are just redefining the topics here. So any doubts? Any doubts so far what we have seen?
No, sir.
Okay. Now what I'm going to do is I'm going to define some functions you are going to define here. So those functions are nothing but it will be defined after the name of the scientist here. So these applications will be there in the image processing. In case of if you go for the statistical signal processing, there we are going to make use of these functions. Okay. So right now I'm going to define the functions I'm going to define here. So some functions. So under that one, the first function is called as the chi-square function you're going to call here. So chi-square random variable. So what you are going to see is under each and every topic, you are going to define the PDF of the each functions you are going to define. So this is the chi-square random variable. So the application we can find in the statistics we can find out. So in order to find out the PDF of the some conditional random variable which will be defined in terms of the exponential terms here. Right? Chi-square random variable. You can see it. Chi square random variable. Done. Okay, so you can take let V be the chi-square random variable. chi-square random variable, chi-square random variable defined as, so chi-square random variable we can define like this here. So it will be equal to the v is the chi-square random variable here. So similar to the random variable x, so this is also the random variable v here. So it will be defined like this. So summation I is equal to 1 to r zi square, where r can take the value greater than or equal to 1, it will take here. R can take the value greater than or equal to 1. So this is how the chi-square function will be defined. Okay, so here zi is nothing but the, it's a normal is Gaussian random variable here. So you can take zi is the, zi is the normalized Gaussian random variable, normalized Gaussian random variable, Gaussian random variable given by, so you know how to define the normalized Gaussian random variable. So normalized Gaussian random variable is nothing but, it mean will be equal to 0 and variance will be equal to the 1. So that one you're going to call it as a normalized Gaussian random variable you're going to call here. So already we have seen this concept, many topics we have seen under this one. Fz of z is equal to 1 divided by root of 2 pi e to the power of minus z square divided by 2. Okay, so we know that this is having the mean. Okay, so the expectation of this one, so that is the thing at expectation of z, so that is the thing at nu z will be equal to 0, and the variance sigma z square will be equal to 1. Okay, sigma z square will be equal to 1 for the that is variance will be equal to 1 for the normalized Gaussian random variable, and also for that one if you are going to take the e to the power of z to the power of 4. So z to the power of 4 is nothing but, it is a z to the square into z square into fz of z. If you are going to integrate here, so that will become equal to the 3 will get here. So this is about the normalized Gaussian random variable which we have seen already. So right now we can define the PDF of the chi-square random variable can be defined like this here. So you can take so just we are going to have the formula is there. There is no derivation of this one. So this it's a derivation given the formula we are going to note down, and we are going to note down the how the PDF of that one is going to vary here. Okay, so that's it. Just we are introducing the concept here. We are going to note down the concept here. That's it here. Nothing else. Okay, so you can take the PDF of the chi-square, the PDF of the chi-square random variable, chi-square random variable v is given by, chi-square random variable v is given by, so it is nothing but f v of v. So it will be defined like this. So I think in your mathematics you have seen the gamma function you have seen here. So going to express in terms of the gamma function you're going to see here. So this will be written like this. Okay, so something like this, we're going to return the gamma function. So it is r by 2, gamma of r by 2 into 2 to the power of r by 2 into, so this is r, this is r to the power of, okay, r by 2 minus 1, sorry, this is v here, v to the power of r by 2 minus 1 into e to the power of minus v by 2, minus v by 2. So you can see, right, f of v is equal to 1 divided by gamma of r divided by 2. So these are gamma function into 2 to the power of r by 2 into v to the power of r by 2 minus 1 e to the power of minus v by 2. So this is how the chi function will be defined here. So we're not going to worry about how it has been derived, all those things. Just we are going to see the formula for this one. So this is for the case v is greater than 0, and it will be equal to 0 for v is less than 0. Okay, done, right? So now you can take where, so this one it is called as the gamma function here. So where gamma of x you are going to call here, gamma of x is the gamma function, is the gamma function, you can take the mean. So we are going to take the mean and characteristic function of this one here. So you can take the mean, variance, and characteristic function, the mean variance and characteristic function of chi-square random variable is given by so for this chi-square random variable we are going to find the mean variance of that one here. So nu v is equal to the r, so that is the mean of that one, and variance of that one will be equal to the sigma v square will be equal to the 2r here. And the characteristic function we can define like this. So pi v of characteristic function is nothing but, so we are going to define with respect to the j omega we are going to define. So it is 1 minus 2 into j omega, 1 minus 2 into j omega to the power of minus r by 2. So this is the characteristic function we are going to define here. Okay. So if you are going to plot this one for different random variables, the plot will be like this here. So for the different values of the r, so this is for r is equal to 3. For r is equal to 3, this is the plot here. So similarly for r is equal to 5, we have the plot like this, and similarly for r is equal to 10, we have the plot here. So this is the plot of the random variable y and x here. Okay, so this is for 5, 10, 15, 20. This is the plot for the different values of r. Okay, so this is the plot of y with respect to the fy of u here, fy of u. Okay, so y with respect to the fy of u here. This is the plot. So the application of this chi-square function. Okay, so in the statistics you are going to find out here the application in case of the statistics you are going to find out, and we are going to consider this one for the where independent Gaussian random variables will be there. So in case of the independent Gaussian random variables, so independent Gaussian random variables, there we are going to see the application of this function, which is called as a chi-square function here. So done, right? So just we have defined the formula for the chi-square PDF for the chi-square random function here. So I'm going to recall. So here we can express the chi-square random variable v can be expressed in terms of the sum of the Gaussian normalized Gaussian random variables we like this here. We know about the normalized Gaussian random variable. We defined the PDF of the chi-square random variable in terms of the gamma function here see defined here, and we are plotted the PDF of that one, corresponding PDFs we have plotted here. Okay, so this is called as a chi-square function. And we are going to see the second type of function, which is called as a student's t random variable. You are going to take the next kind of function, student's t random variable. Student's t random variable. Okay, so these are other kind of functions where we are going to find the where we are going to define the PDF of that one in terms of the t random variable. So getting the concept right. So just here we are defining the formulas for the PDF and introducing a new concepts here. Okay, so students t random variable. So you can take let t be the capital T be the students t random variable t random variable. So here t is the thing, but it's a student's t random variable. So just we are going to call x and y as the random variable. So similarly, we are going to use the t for the student's t random variable. You're going to define here, and it is defined as, so you can define it as t is equal to the. You are going to define this one in terms of the normalized Gaussian random variable, and we are going to define in terms of the chi-square random variable like this here. So z divided by square root of v by r. Square root of v by r. So you know r can take the value greater than or equal to 1 here. So this is r is some parameter here. Some values you're going to take like 1, 2, 3, 4 like that. R is greater than or equal to 1, and v is nothing but it's a chi-square random variable. You can take v is a chi-square random variable. of order, the order of this one will be equal to R, because based on the orders, it is going to extend here. Okay, and Z is the normalized Gaussian random variable. Normalized Gaussian random variable. So right. So just 1 minute I'll take here. So I'm going to give the PDF of this one. Okay, so that's you're going to define here. So you can take the PDF. So 1 minute I'll take here. The PDF of students T random variable. The PDF of students T random variable is given by. So students T random variable PDF will be given like this here. It will be given in terms of the gamma function. So gamma of R plus 1 divided by 2. R plus 1 divided by 2. So divided by, so square root of pi into R into gamma of R divided by 2 into 1 plus T square by R, 1 by T square plus R into R plus 1 by 2. Okay, so T square bar, so it is taken as the power will be taken 1 plus T square by R to the power of R plus. Okay, so this is to the power of R plus 1 by 2 here. So the students T function